Hello and welcome back to the Master Civil Engineering. In this video you will learn that how to draw the influence line diagram for a beam and how to find the maximum positive vertical reaction, maximum positive moment and maximum positive shear from the influence line diagram. Okay, I have been given a question which states that the beam is used to support a dead load of 0.6 kilonewton per meter, a live load of 2 kilonewton per meter and concentrated live load of 8 kilonewton. We have to determine the maximum positive upward reaction at A, maximum positive moment at C, maximum positive shear just to the right of the support at A, by assuming that the support at A is a pin and support at B is a roller. Okay, you can see we have a simply supported beam of total span 35 meter. There are two overhangs for this beam. Okay, the support at A is a pin and support at B is a roller. First, we will find the influence line diagram for the vertical reaction at A using the muller-breslau principle. To find the vertical reaction, to find the influence line diagram for the vertical reaction at A, we will simply replace the pin at A by the roller guide and then we will apply the positive upward force. The beam will deflect to the red line which represents the general shape for the reaction at A. Okay. So support at A, that is pin at A, this is replaced by a roller guide and then we will apply the vertical force equal to the magnitude of the vertical reaction at A. Okay, the beam will deflect to this red line which is the deflected shape. Okay, and this deflected shape represents the general shape for the influence line for reaction at A. Okay, after that, to find the ordinates for the influence line diagram, you will place the unit load at that position where you have to find the ordinate and then you will calculate the value of the function. Okay, for example, this is the beam and this is the influence line diagram for this beam. We have to find the ordinates at 0 meter, 10 meter and this 35 meter. So we will place first the unit load at 0 meter and calculate the value of vertical reaction at A. Then we will place the unit load at 10 meter and calculate the value of vertical reaction at A, and finally we will place the unit load at 35 meter and calculate the value of vertical reaction at A. So when the unit load is at D, that is at 0 meter, we will take the summation of movement about support B equal to 0 to find the value of vertical reaction at A. Okay, so when the unit load is at D, moment of unit load about B, this will be 1 into lever arm which is 30 meter, and this moment will be an anti-clockwise. We will assume that anti-clockwise moments are negative and clockwise moments are positive, so it will be minus 1 into 30. And moment of vertical reaction at A, assuming the vertical reaction at A in the upward direction about B will be AY into 20 meter. Okay, and this will be a clockwise moment. From this we will get the value of vertical reaction at A equal to 1.5. It means the ordinate of the influence line when the unit load is at D is 1.5. Similarly, you have to now place the unit load at 10 meter and calculate the value of vertical reaction at A. So when the unit load is at A, simply if you take the movement about B, so you will get the value of AY equal to 1. Okay, so when the unit load is at A, vertical reaction at A is 1, and when the unit load is at E, okay, again take the summation of movement about B equals 0, so it will be 1 into 5 because this will be a clockwise movement when the unit load is at E, and plus AY into 20, this is also a clockwise movement. From this you will get the value of AY equal to minus 0.25. okay, it means the ordinate of the influence line for vertical reaction at A when the unit loads at E is minus 0.25. After that you have to find, this is the influence line diagram for vertical reaction at AY showing the ordinates at different position. Now you have to find the maximum positive vertical reaction at A. We have been given concentrated live load of 8 kilonewton, dead load of 0.6 kilonewton per meter, it's a UDL, and live load of 2 kilonewton per meter. To get the maximum positive vertical reaction at A, you will place this concentrated live load at A because 1.5 is the maximum magnitude, so you will place it at 0 meter. Dead load, this will be placed throughout the length of the beam, and live load, to get the maximum positive vertical reaction, you will place it on the positive portion of the beam, positive portion of the influence line diagram, that is from 0 to 30 meter. Okay, so maximum positive vertical reaction at A, concentrated live load will be placed at 0 meters, so its magnitude will be 8 multiplied by the ordinate of the influence line, so 1.5 into 8. And live load, this will be placed from 0 to 30 meter, and its magnitude, it will be area of this triangle multiplied by the magnitude of the live load. Okay, so unit load, you have to multiply the unit load with the area of the influence line diagram. So from 0 to 30 meter, area of this triangle is 1 by 2 into 30 into 1.5 into 2. 2 is the magnitude of the live load. And dead load, this is placed throughout the length of the beam. So from 0 to 30 meter, it will be 1 by 2 into 30 into 1.5 into 0.6. And from 30 to 35, this is a negative portion of the influence line diagram. So it will be 1 by 2 into 35 minus 30 multiplied by minus 0.25, which is the ordinate for this portion, multiplied by the magnitude of the dead load, which is 0.6 kilonewton per meter. So maximum positive vertical reaction at A is 70.13 kilonewton. Okay, simply you have to multiply the concentrated load with the ordinate of the influence line diagram, and for UDL you have to multiply it with the area of the influence line diagram. Okay, after that, the next influence line diagram is for the movement at C. So to find the movement at C, again we will use the muller-breslau principle, that is we will replace the at C we will place an internal hinge and then apply the positive moment. The beam will deflect to the red line, which represents the general shape for the influence line diagram for movement at C. Okay, replace the at PC, place a pin and then apply the positive moments. Okay, at A and B, ordinates will be 0 because beam is connected at these points. Okay, we have to find the ordinates at D, C and E. Okay, and to find the ordinates, again we will place the unit load at this position and calculate the value of the function. So this is the general shape for the influence line diagram for movement at C. Now first we will place the unit load at D and then calculate the value of movement at C. When the unit load is at D, value of vertical reaction at A, this is 1.5 as calculated in the previous slide. Okay, value of vertical reaction at A is 1.5. Movement at C, it will be value of vertical, it will be movement at C, value of vertical reaction at A multiplied by 10 minus, since unit load is at D and its movement about C will be anti-clockwise and magnitude will be 1 into 20. So movement at C is 1.5 into 10 minus 1 into 20, which is minus 5. So when the unit load is at D, value of vertical reaction, value of movement at C is minus 5. So ordinate at this position is minus 5. After that, place the unit load at C and calculate the value of vertical reaction at A. So again, taking the movement about B equals 0, it will be minus 1 into 10. Unit load at this time is at C, so movement of unit load about B is 1 into 10 and it's negative since it's an anti-clockwise movement. And movement of AY about B is AY into 20 and this is a clockwise movement. From this you will get the value of AY equals 0.5. Movement at C is simply AY into 10, so it will be 0.5 into 10. This is 5. So ordinate at 20 meter is 5. After that you have to find the ordinate at E. So place the unit load at E. Again, taking the summation of movement about B equals 0 to calculate the value of vertical reaction, which is minus 0.25. And to find the movement at C, it will be AY into 10. Okay, if we consider only this portion, since unit load is at E, so movement about C, it will be AY into C. It will be minus 0.25 into 10, which is minus 2.5. So ordinate at 35 meter is minus 2.5. Again, to find the value of maximum positive movement at C, concentrated live load is 8 kilonewton, dead load is 0.6 kilonewton per meter and live load is 2 kilonewton per meter. So concentrated live load this time will be placed at 20 meter because the maximum positive ordinate is 5. Live load, this will be placed from 10 to 30, and dead load, this will be placed throughout the length of the beam. Okay, so maximum positive moment at C, it will be concentrated live load multiplied by the ordinate, so 8 into 5 plus this contribution from the live load, it will be 1 by 2. 30 minus 10 into 5 multiplied by 2, because live load is placed from this portion 10 to 30 meter only. Okay, because these two portions are negative. Dead load, this is throughout the length of the beam, so for this portion it will be area of this portion multiplied by the magnitude of the dead load. So 1 by 2, 10 multiplied by minus 5, because ordinate is minus 5, multiplied by the magnitude of the dead load, which is 0.6. And for this portion it will be 1 into 30 minus 10 multiplied by 5 multiplied by 0.6. And for this portion it will be 1 by 2, 35 minus 30 multiplied by minus 2.5 multiplied by 0.6. Okay, so value of maximum positive moment at C is 151.25 kilonewton meter. Okay, this is kilonewton meter. After that, you have to find the influence line for the shear just to the right of the A. For that, you will replace the pin at A by the roller guide and then apply the positive shear. The beam will deflect to the red line, which represents the general shape for the influence line for shear at A. Simply at A, you will place a roller guide and then you will apply the positive shear. Okay, this portion will get down and this portion will get up. Okay, this deflected shape is the general shape for the influence line for shear at A. To find the ordinates, place the unit load at this position and calculate the value of the function. So this is the shape for the ILD for shear just to the right of the A. To get the ordinate at 0 meter, we will place the unit load at D and then calculate the value of shear just to the right of the A. So when the unit load is at D, value of vertical reaction at A, this is 1.5, and shear just to the right of A, it will be AY minus 1. If we cut a section just to the right of the A, the forces on this portion DA will be unit load, which is in the downward direction, and vertical reaction, which is in the upward direction. So shear just to the right of A will be AY minus 1, which is 0.5. It means ordinate at 0 meter is 0.5. And when the unit load is at A, again taking the summation of moment about B equals 0, calculate the value of vertical reaction, which is 1. Okay, shear just to the right of the A, this is simply AY, which is 1. Okay, if I cut section just to the right of the A when the unit load is at A, so shear at this portion is 1. Okay, AY, which is 1. After that, you have to calculate the this ordinate at E. So you will place the unit load at E, again taking the summation of moment about B equals 0 to calculate the value of vertical reaction at A, which is minus 0.25. And if you cut the section just to the right of the A, only force which is in this portion is AY. So shear just to the right of A is minus 0.25. Okay, so this is the influence line diagram for the shear just to the right of the A. Now to get the maximum positive shear just to the right of the A, you will place the concentrated live load at 10 meter, because maximum positive ordinate is at 10 meter. Dead load, this is placed throughout the length of the beam, and live load you will place it in this portion, that is from 0 to 10 and 10 to 30, because this portion of the ILD is positive and this portion is negative from 30 to 35. So maximum positive shear just to the right of the A, concentrated live load is at 10 meters, so it will be 1 into 8. Live load is first from 0 to 10. Its area is 1 by 2 into 10 multiplied by 0.5 multiplied by the magnitude of the live load, which is 2. And for this portion it is 1 by 2. 30 minus 10 multiplied by 1 multiplied by the magnitude of the live load, which is 2. And dead load, this is placed throughout the length of the beam. So for this portion its area is 1 by 2. 10 multiplied by 0.5 multiplied by 0.6, which is the magnitude of the dead load. And for this portion from 10 to 30, it is 1 by 2, 30 minus 10 multiplied by 1 multiplied by 0.6, and for this portion, which is a negative portion, it's 1 by 2, 35 minus 30 multiplied by minus 0.25 multiplied by 0.6. So maximum positive shear just to the right of A is 40.13 kilonewton. Okay, so this is how you can draw the influence line diagram for any beam using the Muller-Breslau principle, and also calculate the value of maximum positive movement, shear, and vertical reaction. Okay, simply for concentrated live load, you have to multiply it with the maximum ordinate of the ILD, and for the live and dead load, you have to multiply the area with the magnitude of the UDL. Okay, I hope this solution video was clear and effective, and you definitely learned something new. If you found this video helpful, please subscribe to my channel, share this video, and stay tuned. Thanks for watching.